Okay, here is a problem on a banked roadway, and there are two parts to this problem. The first part is about designing the banked roadway, as they explain here. A civil engineer wants to redesign the curved roadway in the figure in such a way that the car will not have to rely on friction, only on friction to round the curve without skidding. In other words, car moving at the designated speed can negotiate the curve even when the road is covered with ice. Such a ramp is usually banked, which means that the roadway is tilted toward the inside of the curve, and suppose the designated speed for the road is to be 11 meters per second. So that's the desired speed, 11 meters per second or 24.6 miles per hour. And the radius of the curve is 33 meters, right? At what angle should the curve be banked? Meaning, what should be at this angle theta, right? So we are looking for the angle theta. Okay, so what I'll do is, like we should always do in these problems, is to first draw a good free body diagram, right? So we'll draw all the forces that act on the car as it's trying to negotiate this curve, right? So if I draw my forces, there is of course gravity that's pulling it down. There is the weight of the car, mg, right? Yeah, so that's mg, and there is also the normal force from the ground, and that's pushing up perpendicular to its surface. So there is the normal force, and depending on how fast the car is moving, the friction will be either up or down at the incline. And suppose it's going fast enough that I draw my friction force down the incline like this. That's here Fs, right? And I should also note the angle is theta here, right? That's the banking angle theta. And as a result of all these forces, there is an acceleration that's to the left, right? The centripetal acceleration AC, which is v squared divided by r, right? That's towards the center of the circle or center of the track, circular track, right? So I've shown it here as well. While the car may be on a banked incline like that, but it's making a horizontal circle, right? So this one's going in a horizontal circle, so the acceleration is in the horizontal plane to the left. Okay, and if you remember with our earlier inclined plane problems, we kind of rotated the xy axis so that one of them was down the incline, along the incline, and one was perpendicular. We don't want to do that here because the centripetal acceleration is to the left. You see, we always let acceleration be our guide in these problems here, so it's easier if we set one of the axes to align with the acceleration, right? So we'll take the usual x and y axes. So this is along the acceleration, and the one that's vertical, that's perpendicular, we'll call it y. There is an acceleration to the left, that's the centripetal acceleration, but there is no acceleration in the y direction. Ay is 0, right? And just like we have done in the past, anytime you have forces that have angles, we'll have to resolve them into components and then write our Newton's second law equations, right? So if I look at these angles, this angle was theta here. That's the banking angle. So this is also theta that Fs makes with the horizontal, and that's also theta that the normal force makes with the y-axis, right? These are all the same angles. So that helps me break up the normal force and the friction into components. So if I take the components of the normal force, right? So I have n cosine and n sine. This adjacent side here would be the cosine, n cosine theta, and then I have this to be n sine theta. It's getting crowded here, so let me draw it here. So my n cosine theta is this way, and then my n sine theta is this way, and the weight of the car is downward, that's mg. And now I just have to break up the friction into its components, fs cosine and fs sine. This is the adjacent side, which would be the fs cosine theta. I'll draw it here. So that's the fs cosine theta, and then the fs sine is downward. I'll draw it here, fs sine theta, right? So now we have all the forces lined up along the axis, and the acceleration is to the left. That's the centripetal acceleration, v squared over r. So now I'm ready to write my two equations, Newton's second law equations. So when I do that, I have, if I say sum of all the forces towards the center is mass times acceleration, that will give me the total force is n sine theta plus fs cosine theta. The two of them together give the centripetal acceleration AC, which is acceleration is v squared over r. So that gives me one equation, right? And if I look at the y direction, I can say a net force in the y direction is mass times acceleration in the y, but there is no acceleration in the y, so I can write this down as n cosine theta minus fs sine theta minus mg is equal to 0, or I can bring the mg to the other side and I can just say this is equal to mg. Yeah, so let me do that. So I can say this is equal to mg. So that's my second equation, right? And so now I have the two equations that I can manipulate, and my goal was to find the banking angle when there was no friction, right? So these are the general equations that we need for banking road problems. But now we were trying to design the road here, right? So when you try to design the road, you're assuming you're neglecting friction. So if we neglect friction, bad weather day, there's only snow, not much friction available. If we neglect friction, then set fs equals 0. So then your first equation is going to be n sine theta is equal to mv squared over r, and your second equation is going to be n cosine theta is equal to mg. Right? I'm just neglecting these two terms here. So if I do that, I'm looking for theta. I don't want n in my equations. So it's very tempting to just divide one equation by the other. Sorry about that. Let me move this a little more. Not that, sorry. Okay, I didn't mean to move all of them. Get this back here where it was. And this was my second equation. Yeah, that's what was here. Okay, so it's very tempting to just divide one equation by the other. So if I do that, I divide one by the other, then I get the normal force cancels. So I'll say equation 1 divided by 2 gives me normal force is gone, so its tangent theta is equal to mass also goes away, so that will give me v squared divided by r times g, right? Or I can calculate the theta. It's the inverse tangent of v squared over rg, and v was 11 meters per second squared. So I square that. R was 33 meters and g was 9.8 meters per second squared, and if you calculate it, this comes out to be 20.5 degrees. Okay, So that was the first thing. So we have designed the banking road so there is a component of normal force that can provide the centripetal acceleration to the car. So you don't have to rely on friction if the road is banked, right? So, so now that we have that, the second part of the question is this. For the above example, suppose that the coefficient of static friction between the tires in the road is 0.44, right? So this is your mu sub s that's given. For the above example means, take theta to be 20.5 degrees. That's what they're saying. And also take the radius. It's the same radius, 33 meters that we had from part A. And the question is, what maximum speed could the car negotiate the exit ramp to go on that without skidding? Or in other words, we want Vmax. Okay, so so for this one, it's more realistic, right? So we are not neglecting friction. We are taking the friction into consideration, and we have our equations already here, right? Equations 1 and 2. But if we want, as you can see from equation 1, if you're trying to go faster, if V gets larger, you would expect the friction to get bigger, but the friction can only get up to a certain maximum value, right? So we have the static friction can take a range of values, right? 0 to a maximum, and Fs max is given by mu sub s times the normal force. Okay, so we are going to substitute that mu s times normal force into the Fs in your equations 1 and 2, and we'll write these down here, right? So equation 1 will give me n sine theta plus Fs max, right? So what I'm doing here for this part is I'm taking Fs to be Fs max, right? So plus Fs max, which is mu s times the normal force times cosine theta, is equal to mv squared over r, right? And my second equation, doing the same thing, gives me n cosine theta minus Fs max, which is mu s times n, times sine theta equals mg. Okay, and what do we need from here? Well, I should have said V is Vmax, right? This corresponds to the max value of the speed, and that's what I'm trying to find out. So I need to play with these equations so I can solve for Vmax, right? Once again, it's very tempting to divide 1 by 2, so let's do that. So if I divide equation 1 by equation 2, I'm going to take the n outside, right? So n times sine theta plus mu s cosine theta, that's coming from the left hand side of equation 1, divided by the left hand side of equation 2, which is n times cosine theta minus mu s times sine theta, and that's equal to m times Vmax squared divided by r divided by mg, right? So now I can cancel off a few things. The normal force goes away, so does the mass goes away. So if I simplify this, I end up having my Vmax squared is equal to r times g times sine theta plus mu s cosine theta divided by cosine theta minus mu s sine theta, right? That's Vmax squared, or if you want just Vmax, you can say Vmax is the square root of that. So I'll take out that, and this is the square root of all of this. So now if you substitute all the numbers in it and then you calculate it, it should give you the speed, which comes out to be 17.8 meters per second. Okay. There is also a minimum velocity that you can calculate here, in which case friction would be opposite. and your plus would be minus here, your minus would be plus here, and you can calculate the minimum velocity as well. But we weren't asked to do that here, so I'll stop here.